You've just started with that. Well done. Oh, wait, you were muted. Shit. Hello, viewers. Welcome to another Tutor Wizard stream. Although we might be on an ad right now. It's okay. That won't show up in the video afterwards. But that's all right. We have more history of math today. This is another of Adrian's lectures, and he's rip-roaring ready to go with that wand.
That's the Voldemort wand.
That's the Voldemort wand.
This one seems empty.
All right, Adrian, you're up.
All right. Oh, I hear the... Is that a commercial? Should I be waiting? All right, so this time I'm looking for my notes, but I was going to do... Ooh, perfect. That was a play on words accidentally because it was perfect that I found my perfect number notes. I won't prove everything because we'll see how long this goes, but I'll give you the rough idea and then fake it till you make it. And then once we do that, we can ask everybody else if they can come up with, ooh, there we go. There's one place, Lorenzo, remind me, where I'm going to show something about perfect numbers, and let's see if the audience can prove it in the interim part of where I remember how to prove it. I know I've proved it before, but I can't remember right now. It's Sunday morning. What am I talking about? Let's talk about... So we're talking about the Greeks still. Obviously, this is going to be the Greeks for a while. So Greek mathematics. I don't remember where I left off last time because it's been a while, and freaking teaching 4 classes in the spring in 6 weeks might have been a mistake. So it's been out of hand lately. And then my daughter had a concert on Friday, and she had an ortho at the same time, and then I tightened her braces so tight that she puked all night after the concert, and then all day yesterday, and so it's been a freaking weekend, but here we go. The last thing we were doing was these strange... Did I do oblong numbers? Oblong numbers?
I don't believe we did, no.
I don't think we did. Hexagonal numbers. I'll do the figurative numbers. The figurative numbers are a lot of the ways that we could actually come up with some of the algebraic forms, like the sum of the first n integers is n plus 1 over 2. The way that they were doing it was very geometrically. I showed one of these constructions. But what isn't known is that in Euclid's 13 elements, where is this? In these guys, somewhere in there, everybody focuses on the blue one. It wasn't blue, probably. But this one is the one that Mark Solomonovich used when I got taught Euclidean geometry, because he hadn't written the book. He was writing the book as he was teaching the first class. And so we had to use the original 13 elements. Everybody thinks about geometry. But he also, in the other 2 books, had a lot about volumes and number theory. So let's go through a bunch of those, and we'll talk about what the Greeks really liked in number theory. Including, let's do, I want... amicable numbers, amicable, perfect, deficient, and abundant numbers. Hashtags, Octothorpe's. Hashtag. I wanted to do a hashtag because I didn't know what hashtags meant originally, so it was like, can you tell me what a hashtag is? I don't understand. Don't explain it to me. It was rhetoric. I don't want to know. So what are these different types of numbers? I'll talk about the perfect numbers first of all. What they started noticing was that certain numbers were equal to the sum of their proper divisors. I don't know per se how they come up with this conclusion, but it wasn't just the Greeks that had noticed it first, but 6 is the first perfect number, which is 1 times 2 times 3, which is not the perfect condition, but it's this, 1 plus 2 plus 3. So we'll have to talk about positive divisors, and then I'll give you and run through the whole algorithm of how we find all the positive divisors of a given number, and then see if we can find out how he's going to construct these types of numbers. And then there's an open problem. Open problem in these ones. Are there? Nobody knows yet, but if there is, it's like larger than 10 to the 120 or something ridiculous like this. Are there odd perfect numbers? is the question. You might as well just talk in regular voice. The whispering makes it sound like I can't tell whether it's coming from my head or not, Tim. When you whisper, I think it might be my own voice talking to me, and it hurts my brain more. So it's like just speak in your regular tone if you're gonna do it. Shut up back there. I just about spit out my own coffee. So what's a perfect number? I can't remember which one's deficient and which one's perfect. So let me look up the name of this. Just wait, where is this? No, is that one gone? Is that not the one I had? Semi-perfect. Okay, there we go. No, that's not it. I can never remember which one's which. Oh, there it is. I've got it. So let's go through, first of all, what's a perfect number? What's a deficient number? Oh, you're trying to actually work out why OBS wasn't working on the other computer?
Yeah, just a minor technical thing on Discord. Join us on the Discord, viewers. I'll post a link right away.
All right.
Sorry, carry on.
Yeah, so now I had to write them amicable. What are they trying to do with these numbers? What they're trying to do is a perfect number is going to be if, let's call it n is perfect if n equals the sum of its proper divisors. And so this is appropriate that I've used syncopated algebra, so I use words in there to make it easy. If n, I can never remember which one's which, but it's got to be one of them. It's deficient if n is strictly larger than the sum of proper divisors. And obviously abundant is going to be if n is less than the sum of its proper divisors. What's amicable? Amicable has to talk about m and n, and we'll get to that one after, but they're going to be the sum of each other's. They're amicable, or the Greeks actually called them friendly numbers. Friendly. So what are friendly numbers? If they are equal to each other's positive divisors, which means one of them would have to be abundant and one of them would have to be deficient, because I'm going to assume that one's larger than the other one. So we'll get into that one after. But the other two are just parasitic definitions of the perfect number. And then we want to look at how we generate these from Euclid's 13 elements. So this is a theorem that we'll go through. This isn't the first one, but we'll step you through it. That why are you doing that? I've created my own scum. I can't do this, but I clean it off. But let n be a positive integer. Then here's the theorem. Then n is an even perfect number if and only if every one of these pens, I'm going to, if and only if n is equal to, yeah, this one's done too. I need to frickin' find out where all my pens went, and I could have swore I had some that were ready. If n is equal to 2 to the p minus 1 times 2 to the p minus 1, where this guy is called a Mersenne prime. So where we call MP equal to 2 to the p minus 1 Mersenne. There's two n's in Mersenne prime. So what's Euclid getting at here? What he's saying is he has a way of constructing essentially, but there's a problem in there, and that I'll get to in a second. For any prime p, this is called a Mersenne prime if that is also a prime number, but not every prime number produces a Mersenne prime. So we have to check consistently or use supercomputers to run this and show that the only case that we can have where we would have a perfect even number is if both p and 2 to the p minus 1 are themselves prime, but that doesn't always work. I'll get into it with some examples. It's 2 to the 11. I have a bunch of them written down here. We'll go through them first. So let's go through the idea of what he's doing here. This is our main theorem. How do we get at this? The way that we get at this is we're going to start looking at, I don't know what he's doing to come up with this idea, but I'm just going to flesh out all the algebra, and then this is what I'm talking about, where I'm not really the mathematician. I'm not really the mathematician either, but I'm definitely not the historian, and I'm more a mathematician. I'm more worried about not where he got it from and the exact date circa of when he discovers this or what he's doing to get this. This I'm fairly interested in, but also there's a lot of computation in this one, so I'm just going to crush through all the computational values that we have to do to come to this conclusion. First, let's look at 6. 6 is, so let's look at the category of all these numbers, and then we'll start fleshing through in the first ones, and then we'll get into a strategy for finding all the positive numbers for any given number. So if I take the number 2, 1 can't be prime. So if we take the number 2, the only positive divisors are 1 and 2 because it's prime. If I take 3, the only positive divisors are 1 and 3 because this is prime. For 4, we're going to have 1, 2, and 4 because it only has 3 positive divisors because this is a composite. For 5, this is also going to be just 1 and 5 because this is a prime number. And then 6, we're going to have 1, 2, 3, 6. So 4 is a weird one because 4 is the only number that is 4 is 2 plus 2, which is 2 times 2, which is 2 to the 2. And so he has his own quotient pair in there sometimes. And then 6 is the first one that has 4 distinct positive prime numbers or positive divisors. And then what we call proper, I got coffee in my hand, what we call proper is these ones. We don't count the number itself. So you're a proper positive divisor if you proper divisor, let's call it p, if p divides n and p does not equal n. So you can't use n itself. So now what we're saying is if you look at this, 6 is the first number that is equal to the sum of its proper divisors, 1 plus 2 plus 3. And this seemed magical to them. Most of the other numbers don't do this. And then you can see, I just erased it. Deficient is larger than its sum. So all of, yeah, I don't know. That's why it bothers me. I want to be the other way around, but the Greeks defined it first, so then it hurts my brain every time I do this. I want it to be deficient if it's less than its sum, but 5 is deficient. No. I'm just looking at the definition again, which hurts my brain every time. It's deficient if it's larger than its sum. So 5 is abundant because it's less than 1. No, that does make sense. I just hurt my brain. 5 is less than 1 because the only positive divisor here is this guy. So this is called deficient. Okay, that does make more sense. The Greeks were right. And then also most of these numbers are going to be this 4. If you look at this, is equal to what? We're going to have 1 plus 2, which is 3. So this is larger, so this is abundant. So there's a good example. So 4, 5, 6, and 6 is perfect because 6 is equal to 1 plus 2 plus 3. So these are the categories that we're dealing with. Deficient, abundant, and no, I have this wrong. This inequality. It's hurting my brain. Zip, 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 zip. Okay, let me write it out. Deficient is what? This is why it hurts my brain. It's deficient if it's larger than its sum. Okay, that is right. Deficient if larger than sum. There's where we're going to do that. So, and then I wrote it backwards because I really wanted it to be the other way. 5 is larger than its one sum, which means he's deficient. I can't spell either. And then down, now do we have an example of this? You can find the first one that will work for. 4 is also larger than its sum. We're going to have to come up with a number. I'm going to guess this is why the Babylonian stuff started using 60 as their base, because these were abundant, because 12 is now going to be what? How do you find all the divisors? Let's start going. We get 2, 6, and then we get 2, 3. So then what are all the divisors of this? First of all, I'm going to cheat, and I'm going to say tau of 12, and then I'll tell you what tau is going to be tau of 2 to the 3 times 3 to the 1, which is equal to 2 plus 1 times 1 plus 1, which is 6. So it has 6 positive divisors is what that's telling me. And then what are they? They're going to be 1, 2, 3, 4, 6, and 12. Now let's just do this in front of you, where I get what is 1 plus 2 plus 3 plus 4 plus 6. I like to do it like this: 10, 12, 13, 14, 15, 16. Yay! So the sum of the proper divisors is going to be 12 is less, so he's abundant. He has an abundant number of divisors, I'm going to guess. And then they call it having a deficient number of divisors if you are larger than your sum. So this is what they're talking about for deficient. Means that you are larger than your sum of your proper divisors. Every prime has to be deficient because the only divisors are 1 in itself, and you can't use itself. So the sum of the proper divisors for any prime is going to be 1, and so any prime is going to be larger than its sum of its proper divisors. So all primes are deficient, and then we're looking for numbers that are abundant, and 60 has a lot of positive divisors, so it was extremely abundant and an abundant amount of positive divisors, and so they're going to use this one. So 12 is a good example of an abundant number. Any prime number is an example of a deficient number, and then they were looking for perfect numbers. Perfect numbers. What they're going to do here is now, how do they generate and how do they know to create these types of Mersenne numbers and the Mersenne primes? I'm not quite sure, but this is what they're doing. They're taking a 2. All of these are done, so I'm going to try and use a different color, possibly. That one still doesn't work. I should have done this before I was on camera. I tried, but then they lie to you because they have a little bit of juice in them, and then none of them work afterwards. Yeah, there we go. 2, but then is that just at the tip of it, or is it just going to actually have some juice in it? So I want to calculate this. 2 is a prime number, and then I calculate 2 to the 2 minus 1, which is 3, which is a Mersenne prime. And then what the theorem is saying is, when you do this, you're going to get that. Did I do that right? Yes. So P is 2 here in this theorem. P minus 1 is going to be 1. So it says that 2 to the 1 times 2 to the 2 minus 1, which is 2 to the 1 times 3, is going to be the first perfect number. Then what they're going to say is, this is the if and only if was what the theorem says. And how they know the one direction is, if you have a composite number, which I'll do in a second, then this number always has to be a composite number. So let's check the next one. 3 is a prime, and then we'll get 2 to the 3 minus 1 is 7. So 7 is also a Mersenne prime. But what's that going to give us now? Do you see? P is 3. So P minus 1 is 2. And so this says 2 to the 2 times 7, which is 4 times 7, which is 28, is also perfect. And then we go to 4. Is 4 going to give us 1? No, because 4 is composite. What that says is you will always get, and then we're going to have to use a calculator over there because I don't want to do this. the numbers are going to get real big real fast. But then what do I have? I have 2 to the 4 minus 1. Oh, okay, this one I can do. 15 is 3 times 5, so it is not prime. So this will not generate a perfect number. If you look at that, 2 to the 3 times 15 is going to be 8 times 15, which is some number. What is that? 15 times 8, 40. Did I do that right? 120? That seems right. I'm really bad at computing numbers. And I was just up for 2 days with pukiness, and so my brain's not working.
I think you're okay. I think you only think your brain's not working. I think you're okay.
All right, that one's good. So this is what they're saying. If you have a prime number, and then where's the first one? I have my cheat sheet. Did I do this? Yes, where's the first one? But I didn't do it. That's the one where you're going to have to calculate. The next composite, well, we should leave it for the reader again too, but if you look at 5, then you're going to get 2 to the 5 minus 1 is 32 minus 1, which is 31, which is prime. So you get the next one, which is 496 is a perfect number. And then 7 will also give us 1. And then will give us 8128 is a perfect number. What does that give us? 7. 2 to the 7 is going to be 2 to the 7 minus 1 is 127, which is also a prime number, so that will give us a perfect number. And so all the perfect numbers are generated in this process, and you can prove if and only if it doesn't come from that. So they're generating all even perfect numbers have to be of this form that Euclid gives us in his 13 elements, which most people think is all about geometry, but he had a lot of number theory proofs in there. The first one that doesn't work is 11. So what's 2 to the 11 minus 1? 2 to the 11 is 20. No, 2 to the 10 is 1024, so 2048. So 2047 has 2 factors. You can tell me what they are, or it has to have at least 2, but it's composite. Is that right? Yes. And so this is what we're talking about. This is the example. I didn't put it in there, but find a number that divides that guy, and you'll see that he's composite. 13 gives us, and you just start getting huge, huge, huge perfect numbers. But if you're an even perfect number, you have to be generated this way. But the problem is, this is what they're worried about. Not every prime number gives you a Mersenne prime. So it does generate, and it gives you a way that we would generate these numbers, but you can't just say, I'll just pick a new prime number, and then therefore I'll get a new Mersenne prime, and therefore I'll get a new perfect number. So in there's still some mystery as to where the perfect numbers are going to come up with, because you find a condition when given a prime number that the Mersenne number won't be a Mersenne prime. I don't have a condition for this, so then it's still a slight of mystery. Even though this is the only place you'll ever get perfect numbers, not every prime number gives you a Mersenne prime, so not every prime number will give you a perfect number. And so there's a little bit of a mystery in there somewhat. How do you get and guarantee that a prime number will give you a Mersenne prime? Then you could have exactly the complete list of perfect numbers. But for now, we do know how to generate them at least. And then the other question that they could immediately see was, this is even ones. Are there odd perfect numbers? Is there an odd number that could be the sum of its proper divisors? And right now, nobody knows the answer to this. All right. So having done that, what they wanted to know also was, and this will be the other thing I do today, is amicable numbers or friendly. So for the amicable numbers or the friendly numbers, what we're going to do is, instead of, and I'll give the example, I'll cheat and give one. Can you find the first amicable numbers? It's going to be 220 and 284. So what is this? They're amicable if they're the sum of each other's divisors. So what we're going to do with this is, I just wanted to go down the whole of, let's look at finding all the positive divisors of these numbers. So A, says find the prime factorization. Of both of these numbers. B, what we want to do is take each of these numbers n and m and find the square root of n and the square root of m to the, I want to find, did I write that out down right? Yes. We want to find the perfect integers on either side of these guys. So what I want to do is I want to find an a less than the square root of n less than a plus 1. And I want to find a b such that this is less than m, which is b plus 1. And then what we want to do with that is I'll show you that we can use that to list all the positive divisors. I'm going to sneeze. Ooh, come on, stop that. And then what the last one we want to do is show that they're amicable. So, all right, let's do that first. And then I'll have to keep referencing my, oh, that's why I can't see anything. Just wait. Is this up there? Yes. Okay. So how are we going to do this? These are the amicable ones. They didn't stop there, but they said, okay, if we can find the perfect numbers, we can find the even perfect numbers, but we have to keep generating and they get really big really fast. And so they wanted to look at and keep going with this to find if there are numbers which are never going to be the sum of their own divisors, or their numbers somebody must have noticed at some point that there was numbers that would be the sum of each other's positive divisors. So how do we do that? The prime factorization, first of all, we're going to do 220. And so what you want to do is we can use long division in each step if you can't see it, but we're going to divide by 2, so then we would get 110. And then 110, I can divide a 2 in there, and I'm going to get 55. And then we're going to get 5, and then we're going to get 11. And so what is the prime factorization of 220? That's going to be 2 to the 2 times 5 to the 1 times 11 to the 1. So I can get rid of that. For 284, if you can't see it, what I'm doing is every time, if you can't do it in your head, I'm going to divide into 2. So I'm going to get a 1, and then a 4, and then a 1. Is that right? No. 142. So I'm dividing in there. How many times does that go into there? 2 minus. I get a 0. I bring the 8 down. I'm going to get a 4. I'm going to get 8. I subtract. I get a 0. I bring the 4 down. I'm going to get a 2. So this was 2 times 142. If I don't know how to find the factorization of 142, I'm just going to use the 2 divide by 2 again, because I see, what am I also doing in the condition? 2 divides a number if and only if it divides the last digit. So I'm just looking at the last digit in each of these cases. That's why I know there's a number, another 2. I like to start with the smallest prime and then work my way down, but you can make this tree however you want, just dividing numbers in there. But 2 goes into 14 7 times. I get 14, I get 0, and then I bring it down, and that's going to give me 71. Ooh, and then that's going to be 2 and 71. 71 is a twin prime pair with 73, so then we can stop. This is 2 to the 2 times 71. So one of the numbers is going to be deficient, and one of them is going to be abundant. I'm going to guess that this one's the abundant one because he has a lot of positive divisors, and this one's going to be deficient because it's not the primes that are inside it. It's the number of primes and the different kinds of primes that will give you a lot of positive divisors. So what was my... The Egyptians are attacking me. That was, yeah, the Rhine papyrus. Get back to your home. There we go. Oh, someone set off a car alarm upstairs. Now what I want to do is find the square roots of these guys. So what was it? The square root of 225 is 15. And so that one's slightly larger than this. So we know that the square root of 196 is equal to 14. So this is what I'm doing with the second part. And then we want, what's the next one? The 16. The square root of 16 is 256. And then I'm going to use 17. Oh, he goes here. Squish him in there. The square root of 289 is 17 squared, or 17 squared is 289. So what I'm looking for is the positive number on either side of this. So what this says is 220 is between 14 and 15. And the square root of 284 is somewhere between, which one did I just get? 16 and 17. Where were you going, 17? The square root of 284. Why have we done that? Because now no prime less than those guys can be a positive divisor. And so this is the way that I created my, I just erased that. What was that? 2 to the 2 times 5 to the 1 times 11 to the 1. I should put that over here. 220 is 2 to the 2 times 5 to the 1 times 11 to the 1. And 284 is 2 to the 2 times 71. And so now what I wanted was, I know that 14 is strictly less than the square root of 220, and 16 is strictly less than the square root of 284. That's what I wanted with those ones. Now what can I do with that? What I can do with this is we can create a table for each of these, and then I'll leave the last piece to you guys just for fun. I didn't count, but we'll see.
So after you give them homework, they can post their solutions in our Discord.
That's why I was like, I'm trying to do where I want to do everything, but I'm also lazy and I have a million things to do, including chasing down food for my daughter later on today. So you'll see what I'm doing with these boxes, so then you guys can do it. But yes, start pushing it to where I've already done all these calculations. Lorenzo's already seen it because I did the class. But now what I'm going to do in these ones is, this is a way of structurizing. Structurizing is also a word that I just made up, so we're going to put that on this. We got to restructurize this. Structurizing. The way of creating, this is patent pending, the Big Lands method of finding all positive divisors of a given number. Step 1, find the prime factorization. Step 2, find the square root of the number to the closest positive integer. Step 3, write out a table that has all the numbers from 1 to 14 in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Where were you? I didn't even need you. I can count to 14 at least. Still got it. Now what are we going to do? You laugh, but this is harder for me than you think. So now I erased it. Ah, you son of a dirty... I've run out of real estate. Lorenzo, why was this not put up?
You know what? I was just thinking that.
I know. I was like, son of a... I need my side calculations 110. We should have listened to Tim last time.
Yeah, I know.
When he said, let's just do it now. I was like, fuck it. Blah, 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 blah. So the tree will help me. So what I'm going to do is I'm going to ask, first of all, 1 and 220. There's the two positive divisors. I should also do tau of 220. Tau of 220 tells me how many positive divisors I have, so that I haven't missed one in the list. So this will be tau of 2 to the 2 times 5 to the 1 times 11 to the 1, which is going to be what? 3 times 2 times 2, which is 12. So there should be 12 positive divisors in this list. What are they? Well, 1 and 220 is definitely 1. 2 and 110 in the tree will give me 1. Those pairs will give me 1. Is there a 3? No, there isn't a 3. Is there a 4? Yes, and there's a 55 is the quotient pair. Is there a 5? Yes, there is. What's the pair? 44. Is there a 6? No, you can get rid of all the numbers that would have a 3 in them, because we don't have a 3 in them, and we don't have a 7, and we don't have a 13. Etc., etc. So do we have a 7? No. Do we have an 8? No. Do we have an 11? Yes. What is it? Or sorry, do we have a 10 first of all? Yes. What is it? 22. Do we have an 11? Yes. It's 5 times 4, which is 20. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Ooh, 12. Well, that's what the peace of mind is. So those are all the positive divisors of 220.
Slick.
And so this is the AJ method of finding all the positive divisors of a number, because this is a lot harder. At first, I came up with this at first to scare off all the Math 160, all the education teachers. I have to teach the math to the math teachers for K to 12, and we were doing greatest common divisors. And the first way they want to do that, Spider. Hi, Spider. Spider. Hey, where's your... Yeah. Can you see her? Now you can. It's like, I'm not crazy. Spider. Go to your home. What did I tell you? There's a rule down here. When I'm down here, you hide. Otherwise, crush, crush, crush. If you don't hide, or if you do hide, then I'll leave you. That big black one that's in the corner, she's large, but she hides when I come down here, so she's okay. Should I tell Mabel that story? She's never going to watch these. So I had a big horn, one of those big horn spiders, and it got in the house at some point, and it was in the kitchen window, and it just made a huge nest there, and it just sat there. So every morning when we would eat, it would wake up and see us, and then I would watch, and then Mabel had no idea this whole time that there was this giant horn spider every time we ate breakfast. But she knew the rules too. When I'm around, you stay hidden, and then you can do whatever you want after. Let's do the same thing for, now you can see that this is probably an abundant number because it has a lot of divisors, and if you add all of these guys, not including, I need the one, you can't include the number itself because we need the proper divisors. So now what are the proper divisors? You can go this direction and get them in a lexicographical order. So the positive divisors of 220, which are not equal to 220, are 1, 2, 3, no. Read off the table correctly. 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. Those are the proper divisors of 220. If you add that, if you sum these guys, that will equal 284. That's why they're friendly numbers. And so you can show that. Just add that up and do this tail chasing exercise. And you can see that that equals 284, which means what? That's larger than 220, so he's abundant. The deficient one, the other one will have to be deficient, because now if you look at, I can erase this, 284, what did I do? 284, what was the quotient pair now? Damn it. Somebody use their calculator and quickly as a tool. I'll fucking do it.
I think it was 2 to the 2.
No, I don't need that. 284, what's the quotient pair? 284 divided by 2 is 142. 142, and then what do we get? This will be a 2 and a 71, and 71 is prime. So this is 2 squared times 71 to the 1. So this only has, if we look at this, this is going to have, I'm looking at the exponents. The exponent plus 1 is 3. The exponent plus 1 is 2. So this only has 6 positive divisors. But where are they going to be? Underneath the square root. So I'm going to go down there. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Can you 3M my table? I think my table is just brute force to where I just use the square root because I know that if no prime less than the square root divides it, then it won't be in this list. But there's probably a better way of doing this. I probably don't have to do all of them, or just list out a bunch of numbers and they will appear in here. So now I know that in this table, I know that I need 6 of the numbers. Always you're going to get 1 and 284 are for free, and we're not going to use this one. But now I look and I say, do I have a 2 in my number? Yes. What was the pair? 142. So now we already have them. And then what's the last one? The last one is going to be 4 and 71. And so we didn't really need all of that guy, all of this guy, because now what are the positive divisors? The positive divisors of this in the correct order are going to be 1, 2, 4, 71, and 142. So then 1 plus 2 plus 4 plus 71 plus 142 is going to equal 220, which is less than 284. So this is a deficient number. So when you have amicable numbers, you have numbers which are equal to each other's sum of their proper divisors, but they're not equal to their own. And so what that means is one number will have to be, somebody actually asked us in our class, I think, Lorenzo, they said, well, can they both be abundant or deficient? And no, if you think about it for a second, if they're the sum of each other's divisors, one of the numbers is larger than the other one. So if you take this 220 and it's equal to this, if it's sum of its positive divisors is equal to 284, that means he will be
Right.
abundant and the other one will be deficient.
Has to be deficient.
So one of them has to be deficient and one of them has to be abundant if you have amicable
Yeah, I
numbers.
remember looking into this after that is because I think there's a different type of number where the two sums equal the same number, but it's neither number.
Yes,
And
there
then
it goes further down this tunnel, and I
Yeah.
think I have that in the notes possibly too. But that's pretty well, yeah. The magic of what all these abundant numbers, et cetera, et cetera. Well, I just flew through that. That's all I had for today. Do you want me to do more, or what do we want to do?
Yeah, just
Just-
say a couple of words for a second here while we sort a couple of things out on the Discord.
Okay. You want me to run it?
No, you just say, okay, yeah, we're good now. You can say a quick goodbye or what you will.
Yeah, just a second.
I'll also post the link to our YouTube as well while we're doing that, and then people can check out our YouTube page with playlists for. So these videos will be on our YouTube playlist, of course, but also we have stats with Tim. We have linear algebra and multivariable calculus. Plenty to learn. And also, if you have another recommendation for a textbook for calculus, we posted a picture of Calculus Made Easy, but any other recommendation a viewer is interested in knowing. So you can say that if you like.
Yeah, I was just looking in these notes. I have a bunch of, there's semi-perfect numbers and precocious or pernicious numbers and a bunch of the other ones. So I'll go through there. Yeah, I don't know what the pernicious number. Apparently I went down the same tunnel you went down afterwards. Dr. Google has a bunch, but there are a bunch of, ooh, maybe we can do that. Can I draw in Greek? Let me see if I can do this in Greek to where this is what it looked like when they originally did this. Where's this? Where's my pen? In the 13 elements, he has, there is accents on there, and I don't know what those are for. Rho. Is that iota again? Theta. Mu. It's like this is an alphabet or something. I don't know what that last one's supposed to be. I can't even read my numbers. Perfect, ideal, or unique numbers, but apparently somebody can tell me what that says in Greek, and then that's what it originally said in the 13 elements. And then this has nothing to...
Telios. It looks like Telios. Do you got the T, the
And
E,
then-
the lambda, app?
That would be rho.
Oh, so R, Telios, R, Ari.
Yeah.
Oh, Telios, like arithmetic, Telios arithmetic type of thing, eh?
Yeah, something like this.
That's my guess.
I wrote it down for some reason. It was important to me several years ago, and now I can't remember why. But other people were doing this, and then I have in history, a bunch of different people who had tried to carry on what Euclid did. But the amazing part is that, I guess I'll end on there, that the 13 elements, these ones, the book of 13 elements for Euclid, a lot of people just think about the planar geometry in there, but he also did three-dimensional geometry and a whole bunch of number theory. And including that, he did all kinds of things with perfect numbers, abundant numbers, deficient numbers, amicable numbers, etc. So I think we'll end on that. I gotta go.
Sounds good.
frickin'
Let's.
do.
I'm just gonna quickly rate another channel here. Might as well.
Yep.
So we'll do that. So thank you, viewers. I don't know. We'll try this Academy of Useless Ideas. I think they raid us every so often. So let's join that. So we'll start that raid. And then otherwise, thank you, everyone. Let's see. see. Right now, when does this? Let's see, how does this work? There we go. All right.
I'm gonna trip on.
Thanks, everyone.